In this video, we will go over the Aldol and Claisen condensation reactions. We'll start with the Aldol condensation, then talk about the cross-Aldol condensation and intramolecular Aldol condensation, and finish with the Claisen condensation. The Aldol reaction can be broken down into two separate steps. First, starting with two aldehydes, we treat them with sodium hydroxide. Ultimately, they are going to react with one another and create this product, which is known as the aldol product. This is also known as a beta-hydroxyaldehyde because if we focus on the aldehyde here, we have the alpha carbon, then the beta carbon, and there's a hydroxyl group on the beta carbon. So that's where this term comes from. Now, if we take the aldol product and put it in the presence of heat, ultimately we can get rid of this OH group as well as another H and form water, and we can create a double bond that will be conjugated with the aldehyde. So on the next slide, I'm going to show how to form the aldol product, and then we'll go ahead and take a look at the mechanism to form the condensation product. Now we've seen this mechanism before in lab when we were making the chalcones. But we'll go ahead and start with an aldehyde, which contains a set of alpha hydrogens. Now in the presence of sodium hydroxide, which is a base, we can remove one of those alpha hydrogens and create an enolate. Now I'm going to show the equilibrium arrows as being able to go back and forth. Now, once we have our enolate in the presence of a second aldehyde, which I'll put in red, we can have our enolate act as a nucleophile and attack the carbonyl of our red aldehyde, kicking the electrons up onto the oxygen. Now at this point, we have a negative charge on our oxygen. Now the electrons are not going to come back down because there's no leaving group that's capable of leaving. So we cannot have an H or any R groups act as leaving groups. So it will really just hang out in this form until it comes in the presence of water. Now we formed water at the very beginning when the initial hydroxide took the alpha proton. So from here, we can go ahead and protonate this oxygen and create our alcohol functional group. So less than H over here. Okay, so at this point, we have formed our aldol product. Now, in the presence of no heat, the aldol product will be the last step of this mechanism. On the next slide, we'll go ahead and take a look at how heat can cause the dehydration of the aldol product to create the aldol condensation product. Now, this mechanism is showing the aldol reaction with aldehydes. With ketones, because they are more sterically hindered, forming the aldol product is actually not favorable in terms of the equilibrium. So if we take two ketones, such as acetone, and try and form our aldol product, which would look something like this, the equilibrium actually does not favor the formation of the aldol product. And that's because of the steric hindrance involved when the enolate ketone is trying to attack the carbonyl of the second ketone. So because of this, we actually cannot form the aldol product as it is. However, if we were to take two ketones and react it with sodium hydroxide and heat at the same time, it will actually easily form the aldol condensation product. which would look something like this. So while the aldol product cannot be isolated, the heat involved in the reaction will push the equilibrium towards the formation of our conjugated ketone. So this condensation product is capable of being formed. Again, that's because conjugated products are going to be much more stable than the initial ketones, and that will push the equilibrium towards forming this particular product. Now let's go ahead and take a look at the step of the dehydration of the aldol product. We'll use our aldol product from the previous slide. So at this point in the mechanism, we still have sodium hydroxide in the solution. We are simply adding heat to the reaction. Now we have two alpha hydrogens here, which are fairly acidic, so the hydroxide can go and take one of the hydrogens and give the electrons to the alpha carbon. Now we create an enolate. And again, enolates are stabilized by resonance, so they will form fairly easily. Now at this point, the electrons from the enolate are going to come over and form the double bond that will be conjugated with the aldehyde. At the same time, we will kick off the OH as a leaving group. Now, even though a hydroxide ion is not a good leaving group, in this case, because we are forming a conjugated system with the aldehyde, this is a very favorable product. So our conjugated double bonds are highly stable. As a result, it's going to draw the reaction forward. Towards the formation of that conjugated product. Now, our previous examples of the aldol reaction showed two of the same aldehydes and two of the same ketones reacting with one another. A cross-aldol condensation involves two different aldehydes or two different ketones, or even an aldehyde and a ketone reacting with each other. Now, in these types of situations, we have to be very careful about the types of reagents we choose as well as the types of bases we use in the aldol reaction. So in general, using weak bases such as sodium hydroxide or sodium ethoxide generally leads to a mixture of products. So that means we have to consider these two aldehydes here. If our goal is to react them with one another, we have to take into account that they both contain alpha hydrogens. Now the sodium hydroxide isn't necessarily specific. It's not going to know that it needs to choose the alpha hydrogen from the red aldehyde or the alpha hydrogen from the black one. Instead, what it's going to do is it's going to choose the alpha hydrogens from both of them. As a result, we can get a mixture of products. So for instance, if the sodium hydroxide were to remove the alpha hydrogen from the black aldehyde, and this black aldehyde reacted with another molecule of black aldehyde, we would get this product here. If the sodium hydroxide removed the alpha hydrogen from the red aldehyde, and this red aldehyde reacted with another red aldehyde, we would get this product here, which is different. We could also have the black aldehyde have its alpha hydrogen removed and react with the red aldehyde to get this product here, or we could have the alpha hydrogen from here be removed and then it would react with the black aldehyde to get this product. So there's no way to direct the sodium hydroxide to choose specifically an alpha hydrogen, and as a result, you would get these four different products from the aldol reaction. Now this is just showing the aldol products. If we were to add heat to this reaction, these OHs would be removed and we would form the conjugated products instead. There are two main ways to avoid a mixture with the cross-aldol reaction. The first way is to use an aldehyde or a ketone that contains no alpha hydrogens. So for example, benzaldehyde has an alpha carbon here, but there's no H's attached to it. It's only attached to carbons. So therefore, this molecule contains no acidic H's. So if we were to put this in the presence of an aldehyde or ketone that contains alpha hydrogens, such as this one here, when we add the sodium hydroxide, the hydroxide will only remove the alpha hydrogen from our blue aldehyde here. At this point, we will form our aldol product, and it will only be one product. Then adding heat, which I'll show with the delta sign here, will allow us to form our conjugated product. So using one reagent that has no alpha hydrogens will allow us to form only one product. A second way of avoiding a mixture is to use strong bases to create an enolate first. This is known as a directed aldol reaction, and this is a two-step reaction. So what we will do in this reaction is we will take our first aldehyde or ketone and treat it with a base such as LDA. As we saw in the previous video, LDA will create enolates in an irreversible fashion. Once we have created the enolate, we can take the enolate and add it to the second aldehyde or ketone we would like to react in the cross-aldol reaction, such as this one here. So at this point, we have our enolate, and it will easily react with our aldehyde. So this will create only one product. And if we were to add heat to this reaction, we would create our conjugated product. So these are the two main ways that we can use two different aldehydes or ketones and react them with each other in the cross-aldol reaction. An intramolecular aldol condensation can occur when a molecule contains two aldehyde functional groups, an aldehyde or a ketone, or two ketone functional groups. So for example, this molecule here is going to contain an aldehyde and a ketone. Now if we put it in the presence of base such as sodium hydroxide, most molecules are capable of reacting with themselves. So let's go ahead and see how this molecule can react. Now we know that the sodium hydroxide will remove the alpha hydrogens to form an enolate. So with all intramolecular aldol condensations, you want to consider every possible alpha hydrogen that can be removed. So we have two alpha hydrogens for our aldehyde, which I'll label in red. We have a set of two for our ketone, which I'll label in blue. And then we also have another set of three that I'll label in orange. So once we've identified the alpha hydrogens, let's consider what size ring will form if we were to remove each alpha hydrogen and it were to attack the carbonyl on the opposite side. So for example, if the sodium hydroxide were to remove one of these red alpha hydrogens and form an enolate on this alpha carbon, the enolate would then come over and attack the ketone on the opposite side of the molecule. That will form a ring of 1, 2, 3, 4, 5, 6 carbons. Now, if we were to remove one of the blue hydrogens and form the enolate on this alpha carbon, then it could come over and attack the aldehyde. That would form a ring of 1, 2, 3, 4, 5, 6 carbons as well. For the orange hydrogens, we would remove them, form the enolate here, and then it would come over and attack the aldehyde on the complete opposite side of the molecule. That would form a ring of 1, 2, 3, 4, 5, 6, 7, 8 carbons. Now we learned in Chem 226 that the ideal ring size is 6 atoms. So our goal is going to be to form a 6-membered ring. 5-membered rings are also favorable as well. So with all the intermolecular aldol condensations, the goal is to form a 5 or 6-membered ring. So that means our orange hydrogens will not be removed. So now let's consider what will happen if we were to choose the red hydrogens versus the blue hydrogens. Now we know that they would both form 6-membered rings. So the next thing to consider is what type of functional group the enolate is attacking. If we were to remove the blue hydrogens and form the enolate here, those would come over and attack an aldehyde. The red would attack a ketone. Now we learned in chapter 19 that aldehydes are more reactive than ketones, partially because they are less sterically hindered. So that attack of an aldehyde is going to be more favorable than an attack of a ketone. So as a result, the blue hydrogens are going to be more favorable to be removed by the sodium hydroxide. So let's go ahead and draw the mechanism. I'm going to number my carbons to keep track of everything. So the hydroxide will come in, take one of the blue alpha hydrogens, and put the electrons onto alpha carbon number 6. Now we have the enolate on carbon 6. Those electrons will come over and attack the carbonyl carbon number 1, giving the electrons to the oxygen. Now at this point we'll have formed our 6-membered ring. And we have a new bond between carbon 6 and carbon number 1. Now also attached to carbon 1, we have our oxygen that now has the negative charge, and we have a hydrogen. Attached to carbon number 6, we have our ketone. So you always want to make sure to draw in all of the components of the molecule. So at this point, we will protonate our oxygen with water. And we will form the aldol product that now has a ring. Now, if we were to apply heat to this reaction, we would form our conjugated product. So those are all the factors that you want to consider when it comes to the intramolecular aldol condensation. Next, we have the Claisen condensation. This is a similar reaction to the Aldol reaction. However, instead of aldehydes and ketones, we are using 2 esters reacting with each other. This reaction condition involves 2 steps where we have a base followed by H3O+. And once we see the mechanism, we'll see why it's important to have both of these reagents written. Ultimately, we will create a product which is known as a beta keto ester. So we have our ester here, the alpha carbon, and the beta carbon. So on the beta carbon, we have a ketone. So that's how we get this beta keto ester product. The Claisen condensation mechanism can be broken down into 4 main steps. Step 1 we'll call the enolate formation. Now, in our first step with the enolate formation, we will be using the base sodium ethoxide to give us the ethoxide ion. Now, these two portions must be the same. And that's because when we're dealing with esters, esters are susceptible to nucleophilic attack. Now we saw that one of the reactions with esters was base catalyzed hydrolysis. So if we were to use sodium hydroxide with a hydroxide ion, there's a chance that the hydroxide will act as a nucleophile rather than as a base, and it will displace this ester functional group and turn it into a carboxylic acid. So with this, having the same type of functional group here, it means that if we were to have a nucleophilic attack, instead of the ethoxide acting as a base, we would still end up with the same ester functional group. Now focusing on the ethoxide acting as a base, it's going to come in, remove the alpha hydrogen, and give the electrons to the alpha carbon. Now this is an ester, and esters have higher pKa's than aldehydes and ketones, so they're not as acidic. So this step as a whole is not very favorable in terms of the acid-base chemistry. I'm going to draw my equilibrium arrows like this. So it shows that this step is not very favorable. Now with Claisen condensations, it is important to pay attention to the reaction arrows because it's going to explain later parts of the mechanism. Okay, so at this point, a very small amount of enolate will form, but once it forms, it is capable of reacting in the next step, which we'll call step 2, which is the nucleophilic attack. So now our enolate will react with another ester, which I will put in red. We'll come over, attack the carbonyl, and kick the electrons up onto oxygen. Now we learned in the previous chapter, chapter 20, that esters are not very reactive. So again, this step is not going to be very favorable. We have an enolate that didn't form in very high amounts, and we also have a less reactive carboxylic acid derivative. So again, the equilibrium is not going to favor this step. So we'll show a small arrow going forward and a larger arrow going backwards. Ultimately, we will make a small amount of product. The second step of step 2, or the second part of step 2, is the lone pairs on the oxygen with the negative charge are going to come down and reform the carbonyl. We are also going to kick off ethoxide as a leaving group. Now we know that ethoxide is not a very good leaving group, so again, the equilibrium is not going to favor this step. But again, a small bit of product will form. Now if we take a look at this product, this is a beta keto ester, and it looks like the product that would be formed from these two esters reacting with one another. But if we take a look at all of these equilibrium arrows, none of these steps favor the formation of the product. So if we were to stop here in the mechanism, we would actually have an unfavorable reaction that would not occur. So that's where the next steps come into the mechanism. The next steps are responsible for driving the equilibrium of the reaction forward. So our next step is step 3. And we'll go ahead and call step 3 the acid-base driving step. So this is the step that's going to start pulling the reaction towards the completion of the products. So in this step, we're going to focus on our beta keto ester. Now there are two alpha hydrogens here. These alpha hydrogens are highly acidic. That's because they're in between two carbonyls. So typically, these have pKa's of around 9. So significantly more acidic than a typical alpha hydrogen. So now our ethoxide which is our base, is going to come in and remove one of those alpha hydrogens and give the electrons to the alpha carbon. Now we will form an enolate intermediate which is highly stabilized by two carbonyls that it can participate in resonance with. We will also form ethanol as one of our products. Now we learned in the very beginning of Chem 226 that reactions always proceed in the direction of the weaker acid. So we started out with an acid that has a pKa of 9. Ethanol, which is the conjugate acid of our base, has a pKa of around 16. So since ethanol is the weaker acid, we're going to see a forward arrow favoring the formation of our products. Now at this point, we have an enolate and we cannot end with a product that has a charge on it. So our last step, step 4, is our final protonation step. And this is where the H3O+ as our second reagent comes in. So we'll take our enolate, which is resonance stabilized. However, in the presence of a strong acid, such as H3O+, the enolate will easily grab one of the hydrogens and it will restore the alpha hydrogen. Now we already had an alpha hydrogen to begin with, so now we have a total of 2. Now this step is very rapid because we are essentially neutralizing a negatively charged enolate. So steps 3 and 4 of this mechanism are vital to the reaction. If we do not draw steps 3 and 4, then we're essentially drawing an incomplete mechanism that would not exist. So it's important for this reaction to understand each step of the mechanism and how it contributes to forming our final product. So it is vital that the esters contain 2 alpha hydrogens in order to undergo a Claisen condensation with sodium ethoxide. So for instance, if we were to try and do a Claisen condensation with 2 molecules of this ester here, you'll note that each one of these only contains 1 alpha hydrogen. So let's go ahead and consider the mechanism and what would occur if we were to use these type of esters. So again, our sodium ethoxide would take the single alpha hydrogen and give the electrons to the alpha carbon. Again, this step is not favorable. Then we would form our enolate, which would then go and attack another molecule of ester. Again, since esters are not very reactive, this step is not favorable. Our next step is we're going to reform the carbonyl and kick off ethoxide. Again, since ethoxide is not a good leaving group, this step is not favorable. At this point, there's no alpha hydrogen that's acidic enough to drive the reaction forward. There's no alpha hydrogens here, and even though there's a single alpha hydrogen here, it's not in between two carbonyls. It has a pKa of around 19. So it would not give a favorable acid-base reaction. So at this point, the reaction stops. At no point do we have favorable equilibrium arrows, which means the reaction never began in the first place. So we must have those two alpha hydrogens because we need to provide the alpha hydrogen for the last two steps of the reaction. Now, similar to the aldol reaction, there's other types of Claisen reactions. So there's the cross Claisen, and the cross Claisen works best when you have one ester that contains two alpha hydrogens and one ester with no alpha hydrogens. That will really control what is acting as the enolate and what is being attacked. Also, we have the intermolecular Claisen reaction. This is also known as the Dieckmann cyclization. And again, it's following the same type of mechanism as we've seen previously. It's just instead the two esters will be on the same molecule.